All right. Hello, everybody. Welcome to Goals. I'm Mike Hartglass. I'm one of the 6 organizers of Goals, and I want to present this important prerequisite video. And what's going to be about? It's going to be about projections, partial isometries, positive semi-definite operators. And most importantly, about all three, it's going to be spatial versus algebraic characterizations. So much about being successful or sort of understanding, either C star or von Neumann algebras is this interplay between very spatial and geometric ideas versus algebraic formulas that encode them, and kind of being able to bounce back and forth is a very useful skill to develop. And of course, it's a skill that you guys will develop over the next few weeks. But of course, this is going to be a primer to some of this. So let me get into exactly what I'm talking about here. So we're going to first talk about projections. Now, as you may have seen earlier in the notes, maybe I should make it clear here that we're talking about section 8.1 in the prerequisite notes, just so you know where we are. Earlier in the notes, we have this notion of projections. And so the idea is that we have H, which is going to be a Hilbert space. And K, which would be a closed subspace. And so from this, we have our projection P, orthogonal projection onto K. So it's going to be the projection onto K. And how does this thing work? Well, one way to remember this is that projection onto K of Kc is going to be itself whenever Kc is in K. So this projection will fix everything in K. I'm sorry, 1 second. Let me take off the spell check. So this will fix everything in K. And sorry, let me format this a little better as well. And the projection onto K of C is going to be 0 whenever C is in the orthogonal complement of K. And this is enough to define a projection by extending by linearity. And so then we extend, so then we extend by linearity to have something being defined on all of H. That's one way we can interpret this result. Another interpretation of this thing. So let me write that a little bit better. For any C in H, so this does not have to be in K or the complement. This is now just any vector at all in H. Pk of C is going to be the vector in K, which is closest to C. Vector in K, which is closest to C amongst all other vectors in K. Amongst all elements, or all vectors. in K. All right. So we have a very visual idea of what this is doing. But now we want to kind of turn this into a more algebraic characterization. And so we have the following proposition. Actually, this is in the notes. It is a theorem, so I will do my best to copy that correctly. Theorem. So for P, anything in B of H, so any bounded operator, P is a projection if and only if P squared is itself and it is self-adjoint. So you're self-adjoint and you square to yourself. So whenever this happens, in this case, so if the latter thing happens, pH is a closed subspace. pH is a closed subspace of H, and P is in fact going to be the projection onto pH. So, i.e., any self-adjoint operator that scores to itself is automatically going to be the projection onto its range. Okay, let's prove this theorem. And copy it over and we will prove it. Well, 1 second here. Try that again. All right, so let's prove this thing. All right. So going forward, let's assume that P is a projection. So we're going to let P be the projection onto K. All right, so P is going to be a projection onto K. And so note that this means, and we saw this earlier in the notes, this means that the identity minus P, or 1 minus P, is the projection onto K perp. All right. And so let's see how this is going to be useful for us. Okay, so we need to show P squared is P and P is self-adjoint. So to show P squared is P, well, let's note that for any C in H, C we can rewrite as P C, that's projection of C onto K, plus 1 minus P of C. So that's going to be the projection of C onto the orthogonal complement. All right, so let's see what this will imply. This implies that P C is going to be P of P C plus 1 minus P of C, which will be P squared of C plus P times 1 minus P of C. And now we're going to look at the second term and brace it like so. Now we note by construction here that 1 minus P of C is in K perp, which implies that if I apply P to this thing, I get 0. Therefore, this therefore implies, if I look at my above equation, that P C has to be P squared of C because this term is gone. So P is P squared. If I do a projection twice, it's the same as doing it once. All right. Now we need to show it as self-adjoint. So let's show it as self-adjoint. So to show self-adjoint, to show that P is P star, we're going to let C and eta be in H, and we will show we will show that the inner product of P C against eta is going to be the same as C against P eta. So we're going to compute both inner products and show that we in fact get the same thing. All right, so how is that going to go? Well, P of C against eta, well, what is that? That's going to be P of C, and then I'm going to decompose eta as P of eta plus 1 minus P of eta. All right, so that's going to be P C, P eta. Then we're going to add to that P C 1 minus P of eta. Except we're going to note here that this is in K perp, 1 minus P eta is in K perp, and P C is in K. So that's the second inner product is 0. And we're going to conclude that this is going to be equal to P C against eta C. All right. Now, similarly, if I go on the other side, we can play the same game. P C, sorry, C against P eta is going to be P C plus 1 minus P C against P eta, which by a similar argument to the above, is going to be P C P eta. So I skipped the step, but this is going to be similar to above. All right, so sweet. I showed that both of these inner products are in fact P C against P eta. Therefore, this shows that these two are the same. So therefore, this tells you that P is self-adjoint. Cool. So we showed that if I'm a projection, I square to myself and I'm self-adjoint. Or not I, but of course, P, the operator P. Okay, cool. Now we still need to go the other way. So now I need to assume that if P is self-adjoint and squares to itself, then it is the projection onto something. Okay? So we're going to go back this way. And we're going to assume that P squared is P and P is self-adjoint. And so we're going to let K be PH. So we claim that K is closed and P is going to be projection onto K. So we claim K is closed and P is the projection onto K. Okay, well, first, why is K closed? So let's suppose Cn converges to C with the Cn and K. Well, in particular, this implies that Cn, since the Cns are in K, this tells me Cn is going to be P of some A to N. But we can actually do a little bit better than this. I know that P squared is equal to P. So this actually tells you that P of Cn is equal to P of P squared of A to N by applying P to both sides. Let me make it clear to say lowercase p here. Okay. So really we get this for free, but actually P of A to N, P squared of A to N is just P of A to N. So right off the bat, all of this rigmarole tells me that since P of A to N was both Cn and P of A to N was P of Cn, all of this tells me that P of Cn is itself. And so now this is going to be a lot nicer. Because if the Cns, because why? Because since I know P is continuous, so Cn goes to C implies P of Cn has to converge to P of C. Well, P of Cn equals Cn, so this forces P of C equal C, i.e. C has to necessarily be in PH. Right? Because C has to be in the image of P. Cool. So we get for free that if I'm an orthogonal projection, the image was closed. And I should point out something right off the bat that we really had to already leverage the fact that P was P squared in order to run this argument. Hopefully you have seen in the notes examples of operators in B of H whose ranges are not closed. So it's not always guaranteed that you get a closed range, but you do here. Okay. So we now have that the range is closed. Now I need to show that P is actually going to be the projection onto this range. Okay. Well, to do this, let's note a couple things. Let's note that P applied to 1 minus P of any vector C is going to be peak C minus P squared C, which is going to be peak C minus peak C, because P squared is P, which is going to be 0. Okay, so for free, this is already going to be a true statement. And we also note that, of course, I can break any vector, and also note that, of course, any vector C is going to be peak C plus 1 minus peak C. Right. So to finish, so it suffices to show that 1 minus peak C is always going to be in the orthogonal complement P of H because of this breakdown of decomposition. And then this will get us the statement that we want. Okay, so So why is this going to be true? So let's note that if eta is in, of course, pH, this really tells me that P of eta is in fact eta, which will then tell me that the inner product of eta against 1 minus P of any C is going to be now the inner product of P eta against P against 1 minus P C. Okay. And now, if you've been kind of following along, we have heavily been leveraging the fact that P squared is P, and we have not yet at all leveraged the fact that P is self-adjoint. So I figure that now is a pretty good time to do that. So right now we're here, we're going to take P and pop it over and use the fact that P is self-adjoint. So this is going to be eta against P 1 minus P C. But from the discussion above, this guy is 0. And so we deduce that this inner product was 0. Hence, resolving the claim that 1 minus P C is always in the orthogonal complement. And since I can always decompose anything in this decomposition, and in fact, everything in the orthogonal complement will be of this form. And so all these together imply that P is in fact the orthogonal projection onto P of H. I'm slipping in the word orthogonal projection in here because sometimes that is what is said in the literature. The notes will say projection. It says P is the projection onto pH. So I want to make kind of a couple of comments here, and then maybe this will be a good time to end this video. So some comments. So a good exercise, it's another good algebraic characterization. So this is an exercise that is not yet in the notes, or it might be being put in the notes very soon, but it's a good one to do. Show P in B of H is a non-zero projection if and only if P squared is P and the operator norm of P is equal to 1. So actually, substituting in this condition, so having this condition and this will actually force P to be self-adjoint. So that's the thing you're going to have to figure out as to why that is true. So I want to make a comment about this exercise. P not 0 and P squared equals P will always imply that the operator norm of P is bigger than or equal to 1. Bigger than or equal to 1. And this will follow from several things, but we could see it from the submultiplicativity of the norm, because the norm of P is going to be equal to the norm of P squared, but we know that in turn is less than or equal to the norm of P squared. And we know that P is not 0. So I always, for free, get that P is operator norm bigger than or equal to 1. But the magic is that the orthogonal projections are going to be the ones where this operator norm is exactly 1. And maybe another kind of comment or something to think about for the future is that this is a good analogy. So projections we want to think of them as or as the or projections. We're going to think of them as the indicator functions of operators. So they're like they're you want to think of them as like characteristic functions or indicator functions. And kind of one way to see this, um, kind of as an example slash something to for you to work through, that is that if say X mu is a measure space, and Y is say a subset of X, and we'll just say that the measure of Y is not zero. So as measurable subset, measure of Y is bigger than zero. Um, we can view L2 of Y mu as a subspace of L2 of X mu. Um, by extending any F and L2 of Y mu to be zero on X take away Y. So given this, with this identification, try to show that the multiplication operator of the indicator function on Y is the orthogonal projection, or is the projection of L2 of X, L2 of X mu onto L2 of Y mu. Okay. So go ahead and try to show that. Let me just end this with one more bit of terminology about projections, which you will kind of see later. We say that projections P and Q are orthogonal if PQ is zero. And I want to make a note here that this also means that QP is zero because PQ star is then going to be Q star P star, which would be QP. And so that actually then implies that QP is zero. So it doesn't matter which order if PQ is zero, QP automatically has to be zero. So projections are orthogonal if they product to zero, and a projection PI, I, and I are orthogonal is an orthogonal family, or is called pairwise orthogonal. Or let me make sure I get the terminology exactly right. Is pairwise orthogonal if PI and PJ are orthogonal. If I is not J. Um, and so, and an exercise, I believe it's 1.47. And something you can show is that P and Q are orthogonal if and only if PH is orthogonal to QH. And maybe as an example from what I had just written before, if y1, y2 are in L2 of our subsets, sorry, indentations all over the place, my apologies. These are subsets of X, they're disjoint, and both are measurable with positive measure. Then you can check that the multiplication operators of the indicator function on y1 and the multiplication operator, the indicator function on y2, are orthogonal projections. Okay, so I hope these examples are helpful. Main takeaway, of course, going back, is this algebraic characterization of being a projection, namely that you are self-adjoint, you square to yourself, so you're self-adjoint and you square to yourself, and that alone will actually get you the space that you are the projection onto. All right, more will be coming.